Okay, so first we're going to go over an overview of Turing machines and see what they are at a basic level. So essentially, Turing machines are the strongest model of computation that we have. They can recognize the largest set of languages, a lot more than DFAs, NFAs, or PDAs. And to understand why that is the case, we first need to quickly recap what these are and what the drawbacks are. So starting off with NFAs and DFAs, if you remember, these were just state machines. So you had states, characters to read in, and then transitions based on the characters that you read. So the issue with this was that these automatons had no explicit memory. You had no way of remembering or storing information based on what you've seen, and the only thing you can go off of is what state you're currently in. So the states are sort of the only way a DFA can decide where to go, or like what to do. So for instance, if we had uh, this as a character, this string, and say we were currently reading in this character, the only information we have at this point to decide where to go next is the state we're currently in and the character we're reading. So there's no other memory or like thing that like information bank that we can access, which was the issue with DFAs and NFAs. No explicit memory. So that's the reason they can only recognize a set of regular languages and nothing else. Moving on to PDAs. If you remember, these were essentially just NFAs, but with a stack. So they had a stack data structure to accompany it, and this acted as infinite memory. So a PDA could push symbols onto a stack as much as it wants, and then remove them and read them. But the downfall of this, or like the downside, is that because it's a stack, you only have restricted access to the memory. You can only access the very top element or change the very top element. You can't access the other ones. So if this was the current stack of the PDA, we have an A at the bottom and a B at the top. You would only be able to read or change the B, and you wouldn't be able to know anything about the A since it's a stack. So that's the downside. You have infinite memory, but restricted access to it. And that's the reason there's still some languages that PDAs can't recognize and why they're weaker than Turing machines. Okay, moving on to Turing machines. Before we go over what they actually are and how they work, I want to sort of mention the idea and point of a Turing machine, like what it actually represents beyond just, state diagrams and all that. So Turing machines are essentially just an abstract model of computation and what it means to calculate or compute something. That might sound like a bit of bunch of jargon, but the main takeaway is that Turing machines are able to carry out any computation or calculation that humans or computers can. So Turing machines are essentially able to be made in such a way that they follow any algorithm that exists. And what that means is that if you were to show that a Turing machine can't do something, so it's impossible to make a Turing machine to solve some sort of problem, then that also means that we as humans and computers aren't able to do that. So that's just a little tangent, but moving on to the main thing, what Turing machines actually are. So Turing machines are kind of like a DFA, so they still have a state diagram and all that, but they just have a bunch of extra features that make them super powerful. So if you remember, the extra feature of a PDA was this stack they had. So DFAs also have memory as a feature, but that's in the form of an infinite tape. So let me quickly show what that looks like. So this is the tape of a Turing machine. So it's infinite on one end. So this is the infinite end. And this side has an end. Okay, so the tape is segmented, so it's split up into blocks. And each of these is called a tape block. And inside of each block is a symbol. Also, these dots just represent that it's infinite. So each side of each block is a symbol. So when a Turing machine starts reading in a string, so for example this one, what happens is that this string is copied into the tape. So we'd have this at the start. And then all the rest of the blocks, so the blank blocks, contain the blank symbol, which is this. So each of these blocks would just have this. And this would go on infinitely because there's infinitely many empty blocks to the right of the end of the input. So that's the main extra feature of a Turing machine. Now a Turing machine also has something called a read head. So yeah, so sorry, the read head here is the arrow, not whatever the thing is pointing to. So the read head basically shows what block the Turing machine is currently looking at. So if the read head is on this block, then the Turing machine is able to either read or modify the thing inside of the block. So because the read head is on the first block, what that means is that the Turing machine could currently see that zero and it could change it to any other symbol it wants within the tape alphabet. So the tape has an alphabet, which is a finite set of symbols that it can contain. And the read head represents what the Turing machine is currently looking at the tape. Now, what the Turing machine can do is it can actually move this read head left or right as much as it wants. So it could move the read head to the right, left, left. It can do anything. So it's able to freely access the contents of this tape as much as it wants. So it could go infinitely to the right if it wanted to. It can access anything on this tape freely. Unlike the previous automatas, which, you know, like the PDA, they could only access the very top of the memory that they had. So Turing machines are very powerful in the fact that they have this infinite memory that it can freely access and modify as it wants. Now, the other main feature of a Turing machine is the fact that they have this special rule where they must have one explicit reject and accept state. And if the Turing machine enters either of these states, it immediately stops, which is called halting. So if a Turing machine stops its computation, it is said to have halted, and the Turing machine will accept or reject based on which of the states it entered. So what that means is that the Turing machine only stops once it reaches one of these states. So before, for example, with a DFA, you could actually read in a string like 000, and you could go back and forth between the accept state and other states, and you wouldn't sort of stop doing anything until you've read the entire string. So let's just look at how that works. So you start in the 0, read in the 0, go to Q odd, read in another 0, you would go to Q even and this DFA. And this is an accept state, but because it's a DFA, you keep reading in the string until you're finished. So you read this, go to Q odd, read this, go to Q even. And now you're at the accept state again, and this is the point where you stop. Not because you've reached an accept state, but because you read an entire string. So that's completely different to Turing machines, which just immediately stop as soon as they enter the accept state, even once, or the reject state. And because a Turing machine only ever stops when it reaches these states, if it never reaches these states, it won't ever stop, so it will never halt. So some Turing machines on some strings won't stop. It will never give you an answer. So it won't tell you if the string is accepted or rejected because it sort of loops infinitely. And also, one other thing to note is that because these are the only two states that can cause the Turing machine to accept or reject and halt, they're called the halting states. Okay, so just to recap, Turing machines are kind of like DFAs, but they have extra features. The main extra feature is this infinite tape that it has. And this infinite tape is freely accessible by the Turing machine. So the Turing machine can freely access one character of the tape at a time, and you can choose to modify or read that character and like leave it as is. Blanks in the tape are represented by the special symbol, and the Turing machine has a read head which points to the current block it is reading and possibly modifying. The read head can be moved left or right, which means the Turing machine has free access to any part of the tape. And the Turing machine also has one explicit reject and one explicit accept state. If the Turing machine goes to either one, it immediately stops the computation, which is called halting, and accepts and rejects based on which of the two states is stopped in. These states are called halting states, and if a Turing machine never reaches these states in its computation, it will loop infinitely. Okay, so those are the main points, and now we're sort of going to go over an example of this Turing machine reading in a string and seeing what happens. So let's just do this same example. So as we said, when a Turing machine is reading in a string, it'll copy it to the beginning of the tape, and the read head will be at the very start. So let's quickly first go over what these transitions mean. So when you have, say, like A, right arrow B, and then R, so this means basically read in an A on the read head, swap the A with a, sorry, let me just write that. So change it to, and then move the read head in this direction. So a transition like this basically means read in this symbol on the read head, change it to this one, and then move the read head in this direction. So the R could also be an L, which would mean move it to the left. Also, if the read head is on the leftmost position, and you tell it to move to the left, it will just stay in place, because there's nothing else to move to. So, for example, this transition here, if we were to take this transition, we would try to read in a 0, change it to a 0, so we don't change it at all, and then we move the read head to the right. So that's how the transitions on the state diagram work. Okay, so now that we know what the transitions actually mean, let's go over an example of a Turing machine reading in this input. So the input was 0010, which was copied to the tape, and the read head is currently on 0. We start in state Q even, so let's see what transitions we can take. The only one is this one over here. This one tells us to read in a 0, change it to a 0, then move the read head to the right by 1. So let's do that. We read in a 0, change it to a 0, which means it stays the same, and then we move it to the right. Now we're in Q odd, and we're reading in a 0. So we take this transition over here, which tells us to do the exact same thing as before. So nothing changes, we just move the read head to the right. Now we're in Q even, reading in a 1. This tells us to read 1, change it to a 1, move the head to the right. So let's do that. Next one tells us to read in a 0, change it to a 0, and move to the right. So we go from Q even to Q odd via this transition. Okay. Now the read head is pointing to an empty symbol, so blank symbol. So the only transition we can take from Q odd is this one down here that goes to Q reject. We read in a blank, change it to a blank, move the read head to the right. And now, oh sorry, we removed it. Oh no, we didn't. There we go. Okay, so now we end up in Q reject. This is a halting state, and so we immediately stop the computation, and the answer the Turing machine gave for this string is reject. So one thing to note is even though the tape still had a bunch of symbols on it, it has an infinite amount of symbols, we still reject just because we entered the halting state. Okay, so just to reiterate, a Turing machine doesn't need to read in the entire string before it can stop. A Turing machine could read in, say, half the string, and then it would somehow get to an accept or reject state, and at that point it would stop everything, even though the entire input hasn't been read, which was very different to DFAs and NFAs and PDAs where you had to read in everything before you could stop. Okay, now that we've done this overview of Turing machines, we can move on to a couple of definitions that you need to know. So the first thing to understand is that, as we've said before, when a Turing machine reads in a string, it can do three things. It can accept the string, and so it will halt. It can reject the string, and so again it will halt. These are the two cases where it will halt. And the third thing a Turing machine can do when it reads in a string is loop infinitely for an infinite amount of time, and it will never halt. So these are three things, which brings us on to these definitions that you need to know. So a Turing machine is said to recognize a language if it accepts any string in the language. So it will halt and give an accept answer. And if a string is not in the language, the Turing machine either rejects or loops infinitely. So it may or may not halt on strings not in the language. So that's rejections. Essentially what this means is that the Turing machine gives you a guaranteed yes answer on whether or not a string is in the language. But in the case where it isn't in the language, the rejection isn't guaranteed because it may just loop infinitely. The other definition is decidability. So a Turing machine is said to decide a language if it accepts and halts on any string in the language and rejects and halts on any string not in the language. So it gives you like a strict yes or no answer on whether or not a string is in the language, and it will never loop infinitely. So that's that. So if a question asks you if a language is Turing decidable, it's asking you to explain whether or not there exists a Turing machine for that language where these two things happen. So it never loops and it will accept any string in it and reject any string not in it infinite time. So this is infinite time, and so is the reject here and accept. So the only time it goes on for an infinite amount of time is when it doesn't halt. Okay, so we've done these two definitions. Now we just need to do a couple others which are very similar to these ones. So before we said a Turing machine recognizes language if these two conditions hold, and we also have sort of the other end of that, which is a language being Turing recognizable. So a language is Turing, hold some diabolical handwriting, one sec. Turing recognizable if and only if there exists a Turing machine that recognizes it. So just to reiterate, a language is Turing recognizable, or just like in an exam, they might just say recognizable and not include the Turing bit, so don't be confused with that. So a language is Turing recognizable slash recognizable if there exists a Turing machine that recognizes it. And we've said what it means for a Turing machine to recognize a language. And similarly, for the decidability thing, a language is said to be Turing decidable and again, in the exam, they might just say decidable and skip off the Turing bit. So a language is Turing decidable slash decidable if and only if there exists a Turing machine that can decide it. Okay, these are the other two main definitions. And there's one final definition, which is co-Turing recognizability. So a language is co-Turing recognizable. I'm so sorry about the handwriting. If and only if there exists a Turing machine that rejects all strings not in the language. So it will reject and halt if a string isn't in the language, and it accepts all loops if it is in the language. So string in language. So it's just sort of the opposite version of a Turing machine recognizing a language. So here, the loop would with normal recognizability, the loop would happen on the reject like outcome, and here the loop happens on the accept outcome instead. So these are the 5 main definitions you need to know. These 4 are sort of linked to each other, so they're easy to understand. Co-Turing recognizability isn't as important to remember, but something you should still know. Okay, that's about it for the basics, and yeah. One other thing I need to mention is that if a language is decidable, so it's Turing decidable, then it is also Turing recognizable. Because if we look at the definition of decidability for a Turing machine, so a Turing machine decides a language if it accepts any string in the language, which is the same condition that is needed for recognizability. So if a Turing machine decides a language, then this is already satisfied. And if a Turing machine rejects a string, if a Turing machine decides a language, then it will reject any string not in the language. And this satisfies recognizability because the condition is that it rejects all loops. So because decidability guarantees that the Turing machine will reject it, this condition is also satisfied. And so if a Turing machine decides a language, it also recognizes it, which extends to this in the sense that if a language is Turing decidable, it is also Turing recognizable. Okay, next I want to explain what a question would look like, just so you know why we're doing all this. So questions will give you a language and then ask you to prove whether or not, it will ask you to prove if the language is Turing recognizable, decidable, both, or neither. So as I just mentioned, if a language is decidable, it'll also be recognizable. And if a language is recognizable, then it doesn't necessarily mean it's decidable, which means that it'll be impossible for the language to just be decidable. There's only three possibilities. Either it's both recognizable or neither. So just one of those three possibilities. If you think the language is neither of these, you have to prove that mathematically, and I'll show you how to do that in a different video. And if you think a language is recognizable, or it's both recognizable and decidable, what you'd actually need to do is sort of explain at a higher level, like in English words, how a Turing machine that would accept that string would work. So you sort of write out the steps the Turing machine would take to figure out the answer. So essentially you're describing an algorithm in words. That's what you'd need to do. What I mean by that is that they wouldn't want you to draw this state diagram thing with the tapes. The reason we did this is just to understand how a Turing machine works because it's important for when you're writing it out in English. I'll show examples of answering questions in a different video, but I just want to sort of briefly mention what a question actually asks. So, the reason that we're